work so you can share it with colleagues, because we're in for a bit of a treat today. I'll hand back to you, Marta.
Exactly. So I will continue saying that it's a real pleasure to introduce Tugrul Irmak, a mechanical engineer and researcher whose work bridges intelligent systems and the future of kidney care. He studied mechanical engineering at the University of Bristol and then completed a PhD at Delft University of Technology in the Netherlands, where he focused on motion sickness and sensory integration in the brain. After his postdoc, Tugrul faced kidney failure and spent 10 months on dialysis, an experience that profoundly shaped his path. Just weeks after his transplant in 2023, he joined Dr. Karin Gerritsen's group at UMC Utrecht, where he's now working on one of the most ambitious goals in nephrology, developing an implantable bioartificial kidney. So, Tugrul, whenever you're ready, I leave it to you. Thank you very much.
Thanks a lot, Martha, for the introduction. I'll just note there is some slides with sound, and if that sound doesn't play, please let me know so I can talk over it instead of. Can you see my screen?
Yes, we can.
Perfectly.
Awesome. Hello all, and thank you for coming to this presentation called Climb Against Time for a future free of dialysis. So it's 1938. It's a hospital in Groningen, and a young farmer's son comes in, and his face is bloated. His eyes, they can barely open up. He has high blood pressure. He hasn't urinated for days. The urea, which is literally precipitating out of his blood, is trying to find any old way of leaving his body, which includes going out from his eye socket. His breath smells of urine, and there is absolutely nothing that can be done. Fate is cruel, and the young farmer's son is dying. It's 2022, and I'm making my way up and over this easternmost giant of the Alps, Piz Bernina, 4,000-meter mountain. We're going up the Biancograd, which is a meandering ridge of ice, rock, and snow. Once we make it on over this mountain, you're truly in no man's land. Everything is glaciated around you. You're very, very isolated. During the hut, this night of isolation, I was completely wrenched away from sleep by these intense cramps, first starting in my fingers, the fingers that I clambered up these rocks with, moving on to my biceps, and all of a sudden I'm writhing in pain. My partner just quickly springs into action, kind of numb from sleep, not knowing really what was going on. And she tries to stuff magnesium down into my throat. That night was awful. But it was something that I had grown used to, basically. These cramps had become a constant part of my life. It was a consequence of doing something that I enjoyed. I knew I had kidney disease from a very early age, and this is what also kind of propelled me to these climbs, because what better symbolism of vitality is there to be in a place where life can otherwise not be, to show yourself that you're actually not ill. The psychology of illness was of denial, and to live in this denial, I had to show that I could do things. But of course, you can only deny reality for so long. In August 10th, 2022, actually I had a blood test which showed that my kidneys were completely bust. I had an autoimmune disease that was constant for a very long time, but over the span of the summer, it collapsed. So I think, I cannot prove this, but I think I'm the only person to have gone up a 4,000er with severe kidney failure, perhaps severe chronic disease, I don't know. The reason, before this appointment, my doctor actually gave me a call at about 11 p.m. At night, the night prior. And of course, I didn't know it was a doctor because I don't pick up calls from unknown numbers at 11 p.m. But apparently she had the blood results and it was an emergency call. And I was looking forward to actually seeing the doctor this time because I knew that this would be an important appointment. They had recently developed a drug that had gone through phase 3 clinical trials in the US, Nefigard, which would completely halt, at least according to phase 3, which I read, the progression of my disease, which was IgA nephropathy. This drug, as far as I know, is still not available in Europe. So I was waiting for a solution, and that solution was just too late. And so I had to start dialysis. Unlike the young farmer's son who died, I did not have to die. This is because of Willem Kolff, who is the Dutch doctor that developed dialysis in 1943, bringing the first patient back from the dead, essentially. And he built this in a very peculiar time. It was wartime. He built the first machine out of a shot-down aircraft fuselage. And I really see this man as a demigod, because first there was death, and only death. Now there was the prospect of living. Now, the first patient he brought back to life, she was dialyzed, connected to a machine, and then she went home. And then she came again 2 days after, Jenny Schrijver. That was her name. And then she had to be dialyzed again until he could no longer access her blood vessels. So there was nothing that they could do. But at that time, they didn't really know the difference between chronic kidney failure and acute kidney failure. It was just not known. So she died. But dialysis was developed further and it could sustain me. But it wasn't a very good sustenance, I have to say. But let's hear it from the guy. As long as you can hear it, please let me know.
Unfortunately not. Unfortunately, I might have to talk over.
Yeah. Okay, so he says, I had one patient with chronic kidney failure. This was in 1943, basically the story that I explained to you. Yeah, so he again talks about the artificial kidney. And he says that at first it was not accepted in the medical community because, well, people found the idea of taking blood out of the body and filtering it in this kind of external device absolutely horrific. They thought that you could target things better with diet, perhaps. But he said that he didn't listen to those people because he knew, he could see with his own eyes the changes in these patients. So I always bring this guy up in here because I really see him as a visionary figure that deserves more recognition in history. And I feel like if he lived or a little bit longer, he would have gotten a Nobel. But for me, I did peritoneal dialysis, not hemodialysis. And peritoneal dialysis is basically where dialysate is drained into the abdomen and then rather than blood being taken out. It's very easy to say this, but like, for instance, in the first 5 days of this, I write difficulty breathing. Intraperitoneal pressure was so high that I couldn't breathe. It was very odd. When I tried to, I still tried climbing. I was still trying to boulder at this time because you feel physically inferior to other people. You feel kind of cursed. So I wanted to do things. And because of this pressure, anytime I tried to move hard, it would basically seize up my body. It was very peculiar. But in addition to this, I gained about 5 kilos of weight over the course of a week, just because the fluid could not leave my body, the dialysate that was entered into it. And this is kind of what it looked like in my dingy house, cold, without much heating, I have to say, Baxter boxes in the background. Yeah, I would receive about 300 kilos of delivery of this dialysate for a 3-week period. And one room of the house would literally be a hospital. The one thing that I had the most trouble with, Marta notifies me that there are nephrologists here, hello, was that the catheter. And I single out the nephrologists here because it's not something that you talk to your nephrologist about. The physical side of things, the psychological side of things elicited by the physical. So for me, this catheter was an alien appendage, snaking its way around the body. You'd carry it in this belt that you would feel every time that you breathed in and out. It's a constant reminder of disease, basically. This oozing wound. You felt very dysphoric, body dysmorphia, basically. But you also felt a lot of self-consciousness. I mean, you're a human being after all. You have a partner, etc. It was, yeah. And I hear also from other patients that they have the fistula and other forms of external connections to the body. I felt indignified, essentially. After the ambulatory peritoneal dialysis, I went on continuous peritoneal dialysis. And at first, I was hesitant to do this because with APD, CAPD, I could sleep the nights at my girlfriend's house, now my wife. But now on CAPD, on APD, I had to go home for the night. And my partner was this machine that I had to set up every night. She made a lot of sound, snored a little bit. I called her Clara, and my actual partner would sometimes also come round every few days. But yeah, that was it. And this dialysis experience declined over time. I felt at first it was good. My kidneys basically had failed. Before the dialysis started, I was basically experiencing what slow death would be like, your body slowly shutting down. Remember, this was an emergency surgery that they scheduled in last minute. I had to wait 2 weeks for the catheter site to mature enough. So at this time, I was really dying. But after I started, it got better. But over time, again, it got worse as the residual function decreased, as my peritoneal membrane also decreased in quality. I couldn't urinate much anymore. So there was a lot more water retention. In fact, after my transplant, I lost about 12 kilos of fluid over the course of a couple of weeks, 2 weeks, I think. I don't have the graph here, but it's exponential loss of fluid. So it was getting really, really bad. Nausea, etc., etc. When you experience such steep degeneration over the course of just 10 months that I was on dialysis, I can hardly fathom what it would be like to be on this for years, as some people are. And indeed, some people are on this for years and they do okay. But I think this is just survivor bias. We're currently, for instance, making a documentary where we go through some of the experiences in the clinic as well, where this is not the case, where people degenerate over the span of a decade and then they die quietly. Transplantation for me was basically this liberation. I have never before experienced such a step change in my state of existence. So you go into the surgery room feeling horrible. Just before the surgery, I was actually bedbound from fatigue. But then you come out, despite this heavy thing that has gone in your body, you feel good. You feel actually good. And then they wheeled me into my mother's room and held up this bag of urine as if a newborn. It was magical, I have to say. And the time when I left the hospital, I felt true liberation, as if I had just escaped from a cage. And it was a cage. Imagine being connected to something every night. Imagine having this appendage, this alien appendage in your body all the time. Imagine being reliant on an infrastructure to sustain you, basically. You escaped from being an unnatural organism to becoming a more natural one. And that's what I felt. And that's the feeling that I continuously want to hold on to. It's difficult. Life runs its course, but sometimes introspection to hold on to that feeling is good, I think. So dialysis is the current bridge to transplant. And as I said, it's a bridge that not a lot of people make across. So we see that mortality has improved since 95 to 2013. A male 36-year-old, so I'm 30 years old, has a remaining life years of about 12. Great, so I might die if I go on dialysis by the time I'm 45. And if you compare this to the average life expectancy of a normal person, a healthy 36-year-old, you see that this line has remained stationary. And I'm sure a lot of money has poured into research, and the results are little. I think the most success has been had in managing the kind of comorbid conditions that has kind of made this line drift up ever so slightly. But dialysis in its current form is not enough, and it's not surprising because this is 1987. You have the same extracorporeal blood circuit treating the patient, the same kind of hollow fiber design, the same machinery. The only exception that I see is that the displays are analog and the image quality is better nowadays. So I feel that in terms of increasing quality of life and quality of dialysis, we're basically here. We're at this point of asymptote where, yeah, as you see, you don't increase life expectancy much, and yeah, neither do you increase quality of life, because the factors that go into quality of life, aside from the improvements in various kind of physiological parameters, are the same. You're still connected to a machine. So we need to work towards a paradigm shift. That paradigm shift is coming. I think xenotransplantation has a big spot in that future. So the FDA recently approved the first xenotransplantation clinical trials. And this is a good sign for the future. It's also something that I think in Europe that we need to pursue. And I've talked to a few, well, one group in Munich that is doing this. And I think those guys should be supported. But science is uncertain. So the advantages of xenotransplantation is that it can replace dialysis. It has a large capacity. I mean, we're talking about a pig, of course. And there's huge room for improvement. But on the other hand, there's heavy immune suppression, much more so than an allo transplant, zoonotic infection risk, and really we don't want to compromise whatever technology we use to replace dialysis as a bridge to transplantation. We don't want to compromise the future allotransplant. We need a bridge to transplantation. And this thing is currently a resort of last resort, basically. And I don't think that will change very fast or very readily. So at the group at UMC Utrecht, what we're aiming to do is to develop a biohybrid kidney, which can act as a bridge to transplantation, not require this heavy immune suppression. that any cells that are working are actually protected from the immune system. The trouble, of course, with this sort of technology, it's a hard problem. It requires a lot of investment in manpower. But it's a long-term plan we have, from an implantable dialyzer to an implantable bioartificial kidney to a bioengineered kidney / organ. And basically, the technological pipeline that I have in my mind will essentially build up on top of each other. It will essentially lead us step by step towards this endpoint. And you might look at this and say, well, that's ambitious, and long time horizon seems very, very risky and uncertain. Well, this was also the case with the artificial heart, which was transplanted into a human in 1988 or 83, if I'm not mistaken. One of the two. I always get confused there. And again, this was done by this man, Willem Kolff. At least in Utah, he was leading the research group there. I mean, a lot of people were involved in the development of it, especially also the surgeon, Dr. De Vries. And he says here, actually, I hear it. I would really recommend you check out the interview on YouTube with him. Willem Kolff says that he started working on the artificial heart in 1958, and it was implanted in 1983. He says that you have to persevere such hard problems for a long period of time. You have to have, as he says, staying power. So currently in our lab, we're here at this point of developing an implantable dialyzer and also working to get water resorption. So a little bit on the bioartificial side as well, where we include proximal tubule cells inside. And who are we? Well, the lab is of Dr. Karin Gerritsen. And the idea is that the lab has facilities for fabrication. So we have a prototyping lab, a test center, so blood compatibility, etc. Also, it happens to be in an old animal research facility. I say old, it was built some time ago, so it looks Soviet. But we have goat models, etc. So the idea is that we're geared towards very fast transition towards this future. So if I talk a bit about the implantable bioartificial kidney, it's composed of two parts, a hemofilter and an artificial tubule module. The filter itself is basically a membrane, a nanoporous membrane, emulating the glomerular filtration barrier and the other components of it, where basically through convection, you have a lot of filtration that happens. But you also lose a lot of water into the filtrate. In the kidney, about 198 liters passes through per day, and only about 2 liters of urine is created. So you need water resorption back into the blood. And this is where we're working with Cyptec cells, proximal tubule cells, that will do this kind of water resorption. At least that's the idea. Now, the cell side of things is fairly, I would say, low TRL. It's at the stage where we're exploring more of the fundamentals of water resorption and getting it done on a chip system than at the advanced stage. The implantable dialysis filter, on the other hand, is what I think is what we feel is an intermediate step, perhaps. So it's basically something, small device, about the, say, 4 by 7 by 2 centimeter. The thickness should be fairly thin, implanted into the upper thorax and using the same arteries as you would basically for dialysis. It would be subcutaneous. And the aim there is that if you can make a device that's blood compatible enough to function without the risks induced by, well, blood incompatibility, you could have dialysis done without needles. And so perhaps have home hemodialysis as a better, like a more feasible alternative to the current in-center, because one of the most difficult things currently is the vascular access. Either patients can't do it. In our center, for instance, the nurses were saying that about for 50% of the patients, they need to have ultrasound to do this, to do the vascular access, or they won't do it because not everyone wants to stab themselves with a needle, especially a low gauge needle. So for instance, for me, I was even too much of a coward to prick myself with the EPO. My wife did that for me. Of course, you can teach yourself and you can get over it, but a lot of patients don't feel comfortable. So that's our intermediate aim. And the clinical feasibility of this device can be debated. So the market value of such a device can be debated. But I think it gives us a good starting point, show of competence that we can actually make a fairly complex blood interfacing filtration device. That's what we're aiming for. So in terms of specifications, such a device would need thin membrane for free diffusion. We're talking about less than 5 microns. This is on the same order of magnitude as old plate dialyzers, the keel dialyzer. Very narrow blood channels. That's where the magic lies. Blood channel resistance should be very small. High surface area. So for diffusive-related processes, this high surface area is not needed. But for an ultrafiltration device, which you also need an implantable dialyzer to be capable of, you need a high surface area. We need small volume, so as I said, 4 by 7 by 2, and blood-compatible pathings. So we can't have sudden expansions and contractions as in a current conventional dialyzer, where you have blood entry into a cap, and then expansion, and then contraction down into the bundle. So we need gradual blood expansion, and this can be done using a physiological branching law like Murray's law. We need circular/curved channels, so uniform wall shear, essentially. So this is on the device side, and also blood-compatible material, so no contact activation. Currently, the way that we're aiming to do this is through silicon nitride membranes that we're currently developing actually at UMC Utrecht. So 100 nanometer, so very thin, which means that you can have free diffusion. So we're aiming to 3D print these channels down to about 100 micrometers. Currently, we can get down to about 200, 300, depending on the resin. 3D printing, stacking multiple units in parallel, so no manual assembly. And that's the utility of the 3D printing. The reason why current dialyzers are made as they are with the hollow fiber bundles is because you can get a bundle of fibers and you can pot them in polyurethane and that's it. And then you cap it, you have basically leak-free. There's no possibility of leakage. But if you want to have individual flow distribution into such fibers, that's difficult with conventional manufacturing. And that's exactly what you need to limit this turbulence in such a device, which you would need for an implantable. In addition to this, the one thing more hypothetical that I'm working on the side is basically creating the entire thing out of a single material. So single material that is porous. That's a bit more into the future. And basically by mixing zwitterionic stuff like SBMA or heparin, for instance, into the resin, as well as utilizing surface coatings, I think we can at least get something that is fairly blood compatible. So currently we're optimizing membrane coatings. So looking at heparin, PEG, zwitterionic stuff as well as, for instance, GAGs potentially. And what we're really looking for is platelet activation, clotting time, permeability of the membrane after some time, and selectivity of the membrane. And this kind of system allows us to do this in a high throughput fashion. There's a lot of optimization. And the initial prototype that I'm working towards now is first a single unit that can go down to about 100 micron blood channel dimension. And then these stacked as a unit of 4, so on top of each other, just in this cross-sectional CAD model. then to print as a whole unit, as a single monolith. So this is some of the work that we're doing. This is actually production of organ-on-chip stuff for the proximal cell work. So trying to do here is we have two-sided channels, about 300 micron each in depth, and basically on one side there would be a blood analog, and on the other side there would be a urine analog. And what we want to do is basically have an experiment, very simple one, with a membrane and cells in between, where we see water resorption actually happening, where water moves from one beaker to another. So a direct measurement rather than an indirect one, such as looking at gene expression. But I feel, and I will finish soon, 5 minutes, that we're not doing enough. So companies are earning billions. So big dialysis companies are earning billions. So globally, it costs about 110 billion, and there's very little R&D. So if you look at medical device companies at the bottom, Baxter, Fresenius of this graph, you see that the amount of spending on R&D is actually quite low. Perhaps someone will have insight into why this is, or how this is calculated, because I understand that when you're talking about these sort of things, it gets a bit convoluted. One of the things that I did look at myself was patents. So I looked at one company that had filed 200 patents over the course of 5 years. And honestly, most of it was on hardware. How do we optimize this valve and that? Some of it was on fluids, the content of a dialysis fluid, sensors. One of the hype things right now is making things more, user interfaces, basically. And these are all nice quality of life improvements for the device, not for the actual tangible quality of life of the patient. And very little research actually goes into that kind of research, despite the amount of money spent on R&D, because most of that is just development rather than actual blue sky research. And sadly, I think academics are also still captured by this old paradigm. I'm not saying support building out of an implantable artificial kidney. Ideally do so. But I'm saying support solutions that will take us away from this extracorporeal paradigm, whether that be xeno or otherwise. So I think it's difficult to shift the culture to end dialysis. I mean, dialysis has not really changed, as I said before, for a very long time now. There's an innovation roadblock, and the progress is slow. And I think this owes itself to the fact that the kidneys are silent. The public is basically unaware of most of what the kidney does. So for instance, when my kidneys failed, my friends asked me, "Oh, but you have another one, right?" They just don't know. So the kidneys are silent. The suffering endured in dialysis is also silent. That's because people become socially isolated. Generally, your friends, your family even, doesn't like to be around unhappiness. And that's what dialysis is. It's just chronic unhappiness. So I feel like we need to bring attention to what I perceive to be as an injustice. So 2 weeks after my transplantation, I was in Naarden, which is a town in the Netherlands, near Amsterdam. And I came across this statue by accident, by the way, completely by accident. It's the donor monument. It's called The Climb. It's basically a person who's had organ failure climbing out of this pit of misery. And I thought, why don't we do something exceptional and climb? Because the monument is called The Climb. So this summer, I will be doing 41 peaks above 4,000 meters through hard routes that can result in fairly grim consequences. And yeah, so these are some of the mountains that will be encountered during that process. But this isn't only excluded to me. Lucy, for instance, will also be participating by completing a ultra marathon. And there are about 35, 40 participants now doing their own stuff, from small hikes to the big ultras. There's actually one donor. He donated his kidney to someone he did not really know well, that will be doing an ultra as well, to show that you can be a donor and still be damn fit, and he is. So I need your help. We need your help as well. So there's the LinkedIn page, Climb Against Time, Instagram, YouTube. If you just Google Climb Against Time, it will come up. And I would really, really appreciate it if you subscribe to one of these pages, or just connect with me on one of the platforms. Because basically at the end of this presentation, if I just give this presentation and then call it a day, that's it. That contact is lost. But if you follow these things, I think it will really help. In addition to this, actually, I'm doing a lot of public outreach to boost the whole profile of kidney, and especially dialysis and kidney failure. So today there was an article on Het Parool. This is an Amsterdam-based daily newspaper, on the New Scientist as well. Was also featured on the national broadcaster here, and also there'll be another one on the RTL. And yeah, so doing a lot of work. This is the web page that you can also visit for more information on this. Yeah, if you feel like there's any way that you can help, or if there's any way I can help you, just let me know. And thanks for listening. And I'd love to take some questions, technical or otherwise.
Thank you very much, Tugrul, for this amazing and inspiring talk. So, first of all, I would like to say or welcome all our sustainable champions that are connected today, and just remind that we have a meeting on the 15th of May, where we will update them all the news related with the UK Sustainability Kidney Care Project. Anyway, so I don't know if anyone would like to ask some questions from the public, because I don't see you all. But just beginning with the first one, Tugrul, I would like to ask you, because you have mentioned that you have this background in intelligent systems. How does this background influence you, together with your kidney problem, your approach to challenge all these matters related, all these problems related with artificial kidney design?
Yeah, I think it's an engineering, well, I'm a mechanical engineer, and I see things more of an engineering problem than not. So if you have cells on a membrane, I think you have a complex membrane, rather than immediately concentrating on the fact that they are cells. I mean, they're complex membranes that have their own requirements. And I think engineering leads itself quite naturally to, let's say, multifaceted systems, interdisciplinary kind of work, basically. So I think that's how it's kind of influenced it in that sense. And the disease, how it influenced it, well, I didn't want to be working on anything whilst being connected to a machine, aside from getting myself off that machine.
And I think we have now one question in the public before I go to the next one. Gopinath? Yeah. Can you?
Yes. Sorry, yeah. My mic was muted. Hi, good evening. Myself, Gopinath. I'm from India. That's a good, interesting initiative which you have taken. And if it was really good to know that dialysis will be. But I have one question technically. The
Yeah.
kidneys, which we are doing for artificial membranes, has to be filled. So you told that from 200 decimal you are going for 3D print for 100. So it like an device, like heart valve device, mechanical heart valve device. So we are
Yeah.
placing into the pelvics, right? Either into the near to
Yeah.
the. So in that case, do you know a surgeons and the reference of the surgeons and the blood compatibility? I mean, the rejection factors. Will you consider about the rejection factors?
Yeah. So we've talked to vascular surgeons about possible sites for implantation of such a device. What we don't want is for that device, because it needs vasculature and enough blood flow. We don't want that to compromise potential sites for a transplant, because there's only so much connections that you can make reliably, then it gets complicated. So one of the ideas that we kind of came to now was implantation in the thorax. So kind of like a pacemaker, to use the same blood vessels as that are currently used for hemodialysis. So that would be, and it would be a subcutaneous implant. So one of the things with any kind of medical devices such as this is that what happens if it fouls? Let's say your device loses function. If it's subcutaneous, you can replace it. It's also, if it's subcutaneous, you can take it out if it's not functioning as you desire, or if it becomes a complication. And in terms of rejection, so for a device without cells, obviously you can have clotting response to it, or like foreign body response to it.
Yes.
With device with cells, the idea is that the cells are protected enough on the cell side by about 200 nanometer pores. This would prevent immune cell infiltration, but they may still be susceptible to, say, certain complement proteins. But I don't know. We're not at the stage to know whether that would be the case.
What are the proteins? Yes, what are the proteins there? Because my main point is the flight and fight response of our body will definitely reject the system when it was not. So usually we'll do the allograft, or we will give the medications to reduce it, to stay with the immunocompliance, so immunosuppressants. So that's why my major concern is.
Yeah, because there's no direct cell contact, we're hoping that such a device would have less of this issue.
Okay.
Tugrul, can
hope
I
for the best. I'm glad.
Sorry, can I ask you to stop sharing the screen, Tugrul?
Yeah.
Thank you. So I don't know if I have interrupted the question. Were you gonna?
No, it's okay. We are good. We are good. Yeah, it's was done. A little bit of more efforts will be there. Definitely, it's not worth of billions of investment, but it was saving more of life, because none, as you said, that the R&D of many international companies, because the leading factors are companies like Baxter and Freshness are still behind the lines. So it will be a breakthrough in the achievement of saving lives. It's a major impact on the livelihoods of all the people around the world. Thank you. Thank you for the initiative.
Thanks a lot.
So, while there is another question, I can see that you have done quite a lot of progress, and this is also a question for Karin. Quite a lot of progress in the bioartificial membrane, and then the next step would be the bioartificial kidney. So how far do you see that we achieve that? Because what I would like to understand is this bioartificial membrane that you want to implant in the thorax. How would that work in terms of dialyzing or doing the process of both processes?
Yeah, so for an implantable dialyzer, there is no bio component, aside from the component that is interacting with the blood, so to speak.
Okay, yeah.
For the full bioartificial kidney, there would be a cell component, of course. And the idea, so currently the state of research there is that we've had these cells in, well, I say we, at the University of Utrecht, they've had them in culture conditions for, I think, up to a month, perhaps more. And then, but these are static culture conditions. Then you start to see phenotype changes. They start to see phenotype changes. But I hope that under kind of non-static flow conditions, this will be less of an issue. The one thing that is, of course, that's a challenge currently is that if there is damage to the monolayer of the cells, how does one repair that? These cells actually propagate at a certain, so they start dividing at a certain temperature. It's actually lower temperature. They have this oncogene. So currently we also are looking at ways of actively regulating this temperature on the surface of the substrate. But yeah, that still remains to be seen currently. Yeah, so at this point in time, we're looking to bring these cells onto a flow device to do basic water resorption test. With that test, we can say that, okay, per centimeter square of cell-laden area, we get this much water resorption. How much area do we need? And that goes towards enabling device design.
Good, good. I think Lucy has a question. Lucy?
Yeah, just a quick one from me, really. Tugrul, I was fortunate enough to see you speak in March at our General Assembly at Kit New Care. And I'll be honest, I came away completely inspired and blown away by you. And I'm really glad you could come today. For me, I'm thinking you're taking on such an enormous challenge. What I'm doing is, half a day. You're taking on such an enormous challenge. Where do you get your grit and determination from? And how do you keep going? I think it's truly inspirational. I think a lot of us could do with some of Tugrul in us.
Well, I mean, at some point you put yourself into a corner and you're pointing the gun at yourself. If you say you will do this thing publicly loud enough, you have to do it.
Very true. But what keeps you going when things get really hard? Because I'm a runner and things get hard. But how do you keep going for that long? How do you dig?
Well, I mean,
deep?
it's also through a long period of time. I mean, I feel like the challenge itself is manageable. But I mean, I've never really been to the Alps for such a long period of time. So it remains to be seen how manageable it will be. But yeah, I don't know. I guess there's also the survival factor. Because I see a future basically as there are two futures. One is where eventually I go back on dialysis because the lifetime of a transplant kidney from a live donor is 20 years, some people less, some people more. Or there's a solution that makes it so that doesn't happen. And when I think, so if you're working towards a solution, you just got to do stuff.
It's amazing. It is. You're so inspirational. Thanks so much for joining us today. And I'm sure everyone else on the call is probably feeling the same. Are there any other questions from anyone else on the call? Be brave, or you can type it in the chat if you're not feeling brave.
While other question arise, I just wanted to ask you, through all this process of creating this artificial membrane, or the next step, what are the main barriers that you have been facing, all your team?
Yeah. So some things in research, and I think a lot of people will appreciate it here, require a lot of elbow grease. So you just need time to kind of sit down and run the experiments. And sometimes if an experiment takes half an hour, it will take half an hour. There's nothing you can do to make that faster. And when you're talking about key scientific challenges, so blood compatibility, where you're optimizing a lot of the coatings, or looking at, just optimization, takes a lot of time. And there's severe manpower shortage in going through these optimization procedures that you need to do to develop a device. So I think that's one of the main challenges. The other challenges, of course, the scientific challenges are quite hard. So, and hard challenges, I think, generally require international effort. So, for instance, I was in the intelligent vehicles group in Delft, so we were trying to build an automated vehicle. In fact, I'm here today.
Oh.
And the vehicle's right there.
Yeah.
This is the vehicle that they're trying to make automated right now.
Mm.
It's my old group. But these guys are basically one of hundreds of research groups on trying to create a car that drives itself. And tens of companies that are investing billions into making that happen. That's a hard technological problem as well, and they've kind of succeeded. So what I think is challenging is being in an academic environment where you don't have people working on the same problems. So you don't have people questioning you and working, like looking up to what they've done so you can copy it and maybe do it better. There's less of this turnover, and I think we need that. And yeah, that's also one of the aims of this kind of this initiative, you could say.
So you think you are quite close to finish this prototype of artificial membrane, or when do you think it will be a reality that you will be able to try it in patients?
Okay, those are two different questions, I think.
Yeah.
So a prototype, I hope next year, because one thing that is required is small channel dimensions, which is what we're working towards with our resins, basically. We need blood compatibility on the resin side, which is also something that we're working towards. And there are ideas, like concrete ideas. Okay, we need to add this much of this to get there, kind of. And then I'm pretty confident that we will create a prototype. It's long-term blood compatibility. I cannot say what that would be for that prototype. So we have means of testing it in the bench, but bench blood top testing does not tell you how long it can last in an organism, because just from the tubing that is in that system, you will, and the lack of actual physiological interaction in an organism. If you implant it into a goat, you have perhaps kilometers of vascular stuff that your cells are interacting with in addition to your device. So I feel like we will develop a prototype by during next year. I cannot tell you how well that prototype will perform in a long-term blood compatibility test in a preclinical trial animal. That's something that we have to see. And this would be prototype for an implantable dialyzer. The cell side, we need more information still.
Wonderful. And I have just my last question, because I don't see any other ones, and it's related of you as someone who breeds both worlds, the lab and being a renal patient. How do you think patients will perceive this idea of an implantable artificial kidney?
Skepticism.
Okay.
Yeah, so I was a patient. And I know the work, for instance, at University of San Francisco, I think, at the artificial kidney there. And as a patient, you look at it, you're like, okay, 2 decades of work and nothing came out. But of course, again, as I said, I think we lack the international kind of community for the development of this. Yeah. So it's no surprising that one group working on it has not developed something. That's not surprising. But also skepticism, because you don't want to get your hopes up, right?
Yeah.
That's one of the things. You don't want to get your hopes up.
Well,
yeah,
that's our work together, to work together to prove that it can work. Well, thank you so much for such a wonderful talk and inspiring. I say again, I don't know if Karin is still connected and if she wants to say something else, Karin, or I don't know if she's connected. Anyway, well, well then I will just remind for, Karin, you want to mention something?
Sorry. No, actually, I have nothing to add to this. Actually, the story is, I think, very clear. And, I have a lot of respect for Tugrul, how he does this. And
Congratulations again, Karin, with all the work that you are doing. So just for all those connected and still haven't become a sustainability kidney champion, we have just put in the chat the sign up form in case you want to develop a kidney unit, as I say, sustainability champion, and we'll be very pleased if you want to join our community. So I don't know, Lucy, if you want to add something else?
No, just to add an enormous thank you to Tugrul and Karin as well. And just to reiterate, please do join us. If you haven't signed up to be a sustainability champion yet, please do join us. Lots of free resources and access to brilliant people and like-minded individuals to really work together on sustainable kidney care. So please do join us. The links are in the chat there. We have our first forum meeting on the 15th of May, only a couple of weeks' time, where we're very exciting to be launching the benchmarking tool, first of its kind in the UK. So please do join us. And thank you. Thanks, Tugrul. Nothing more from me, other than I better start running a bit more.
Thanks a lot. Have a lovely day.
Thank you. Thank you very much for all those who have remained connected, and see you about in a month's time in the next network meeting. Thank you, Tugrul. Thank you very much.
Thank you.
Bye-bye.